Perfect. Okay. Hi, everyone. My name is Wadim. I was already introduced, I'm a theoretical physicist, and back in another life, I was an elementary particle physicist and a gravitational physicist. So I dove into black holes, and then I came out again. That's, by the way, it's a physics joke. So today, I'm here to present to you a project that we did at Bundesdruckerei. And Bundesdruckerei is the federal printing agency. And before I hand over to Janine, who will explain to you all the really technical things of substance, I would like to answer a question that is probably in everyone's mind right now. What is the federal printing agency doing with quantum? Okay, there's already a nodding. Yeah, of course, of course. So let me explain to you why we do this. So first of all, Bundesdruckerei is probably in everyone's pockets. It's the ID cards, it's the cash, or that may be digital certificates. And we are responsible to produce these things, these products, to maintain them, and to verify their security and guarantee their security. And security is a subtle art. Security is a cat and mouse game. And the trick is to always be the cat. So how do you manage to always be the cat? Well, you have to be aware of the risks around you in the present, but also in the future. And this is a challenge. This is a really big challenge. For that, you need a lot of innovation. And we in the innovation department, we are looking at disruptions, at coming disruptions, at present disruptions. And well, one of those disruptions is quantum, right? That's why we're here. So we at Bundesdruckerei are managing a project with the Federal Ministry of Finance. And there we are supposed to evaluate the risks and potentials of quantum technologies. And quantum computing is part of that. And for us, a big focus is sovereignty. And sovereignty means we need to be able to look at the truths, at the lies, at the challenges, at the easy things, so at everything at once, and do it without a veil, or do it fully. So what we did is we started a project where we looked for a partner and to get an insight, a truthful insight, and a really, really transparent insight into quantum computing. And benchmarking is, of course, one of those topics that are absolutely important for sovereignty. And we are absolutely happy to have found one. And maybe one more thing. So it should be clear why we do benchmarking. I think everyone kind of understands and feels that benchmarking is very, very important for sovereignty, for security, for everything, because we kind of monitor the risk value that quantum computers bring day by day, year by year. But let me tell you maybe two things about benchmarking that are not that popular, and maybe something that may motivate you to also do benchmarking. So benchmarking is one of the most interesting things you can do in quantum at the moment, and maybe also in the future. Because benchmarking is a very, very intricate art and requires pretty much all fields of quantum to be used. If you are doing quantum algorithms in any way, you probably can do benchmarking in some way. So it's a super exciting field, and many, many different fields contribute here. And there's a lot of publications, and these publications, they have a little bit of a subtlety behind them, because usually it's very hard to reproduce these results, be it because of money or time, access. So yeah. So another thing about benchmarking is even more important for many of you here, if you're in the industry, benchmarks set expectations. So if someone writes a tender and you apply to this tender, there might be deliverables in these tenders. And these deliverables might be inspired by current benchmarking results, which may or may not be possible to deliver at all. So these benchmarks, they better be good and meaningful, right? And we try to do exactly that, to do something. And as innovators, we try things. And we are open to criticism. And especially we are open to try even more things. But before I talk too much, I already stole so much time of you, Janine. Please, go ahead. Janine.
Yeah, thank you very much. Yeah, as Wadim said, benchmarking is really important topic to have realistic expectations and also, yeah, to discuss it and to test yourself, to have something which can be tested abroad different systems. And yeah, I want to highlight that we have not the perfect recipe for the benchmarking of QML here. I think many of you know that. This is not yet the time for that, but we started with this, and I think it's important to start having some attempts, talking about them, improving them over the time, because it's such a field where so many things happen. So one has to start with something which is adaptable to all the changes. And yeah, let me first introduce next a little bit, because I think maybe some of you heard about it, but maybe a lot of you not yet. Um, we're a startup building trapped ion quantum computers, and we originate from the University of Mainz, the group of Ferdinand Schmidt-Kahler, who's into this topic of quantum optics and quantum computing for a very long time already. And yeah, also lots of funding, different funding things here you can see at the university. And then, yeah, we started 2 years ago and stepped into the startup part, and now we're building these trapped ion quantum computers, starting from the trap, but also up to the software stack. And we really enjoy making them usable and testing them and doing this in these nice projects as here. And yeah, I think I wanted to motivate it a little bit, but in this audience, I don't have to motivate too much why we need quantum computing or why machine learning is interesting and why the combination is especially exciting, I think. But there are so very many open questions, and some of these questions are: how can we make use of quantum machine learning? How can we make like these first first examples, playing around with it? We learn a lot, but it's so many parameters. There's really a lot of space on the classical optimizer side, on the quantum ansatz you're using. So many things to explore, but how to compare if one thing was better than the other. And this is where our first draft here for this benchmarking steps in. So the inspiration came from application-oriented benchmarking, which yeah, you can see here this paper. There is also reference to volumetric benchmarking, the predecessor of this. So the idea is that you have kind of a nice explainable picture visualization, because visualizations are really important to see how a certain task or algorithm performs on a certain machine when you compare scaling it up, because we have to start very little, but we have to scale it up on the long run to make it a really usable project where at some point it is we might get an advantage, but we have to start with the small parts, of course. And the idea is that you have a scaling of the width, which is the number of qubits, and the depth, which is the repetition of a certain sub-algorithm. And then you have some score, which is indicated by a color, which is between 0 and 1, and you define how this score is calculated. And we can zoom in one of these squares, and then we have this radar plot, which you see in the middle, which explains a little bit what parts we're using here to calculate the score. And I want to very briefly give you an impression what we went for now, which is something like the number of qubits, the depth, the number of iterations. Here in this example, if you use a classifier, you might want to use something like the F1 score. It's like how good did I perform, which can be if you're doing something else compared to a classifier. It could also be something else on this thing. And the magic parameter in quantum computing that defines how large is the distance to a stabilizer state. And that is the interesting part where it gets like how much do you profit kind of from your quantum computer? Because if you would have just stabilizer states, you could very efficiently calculate it even on or simulate it even on a classical computer. So it's kind of a measure for how much do you gain from doing it on the quantum computer, which I think is kind of important to include it, because there's always the question for this very specific application, is it actually worth? Because quantum computing, it is really a lot of computational effort right now. It is also expensive. So for this very application, is it good to run it on a quantum computer, or maybe not yet? Or maybe just starting from a certain size of the problem. And and we scaled it with the maximum number of qubits and the max depth, because that's also a consideration. If you book or use a very large system and then use only very small part of it is also not really efficient, because it might be very expensive, and you might the large systems usually have a less high fidelities and so than the smaller systems, if the small system has enough resources for your application. And yeah, then you get these nice visualization. And here's one example of this recipe, which I show you now some more also measurements we did on the trapped ion quantum computer. So we focus now, we wrote a Python framework, and we heard a little bit about frameworks. It also has like modular parts, and you can go in there with different quantum machine learning applications. We implemented also a few ones, but yeah, that would be out of the time frame here. But in the Q&N, I want to dive a little bit deeper. And there we implemented some of the basic encodings and ZZ feature map ansatz. But this is also the option to upload a custom ansatz. So you give it a circuit for the ansatz. And that is what we did here. So we have this re-uploading ansatz where you see the circuit here, because it performed a little bit better. We run this then also on the trapped ion quantum computer. And first you can look into it with the simulator. How does this behave? How does the metric look like? If you run it, that you have some expectation. And especially with the small circuits you can run on nowadays quantum computers, you can still do that. You can put it on the simulator easily, and you can see what is my expectation. And yeah, on the left you see the full metric, but on the right you see weighted. So it's also built in that you can weight every individual entry of this radar plot for the score, so such that you get an impression how this influences your final result.
Maybe, Janine, second. This is a big question mark, this graph. So there's something different happened from 1 qubit than for more qubits. Sorry, Janine, just wanted to cause.
Yeah, sure, and that's I even highlighted that a little bit.
I know.
Side, yeah. Because this is really a question. You see it scales. This is still on the simulator, but later on you see it. It's also confirmed on the trapped ion quantum computer. It had the very same behavior. That you see the depth, like how large you make there your circuit, and then the number of iterations. And for a single qubit, it scales like, okay, you make it deeper. You need more iterations to converge here. But for 2, 3, and 4 qubits, that's not the case anymore. Like it's flat. And what comes in there? I mean, for a single qubit, you don't have entanglement yet, but it's still an open question to explore what exactly happens there. And the execution duration, that increases still, because it's when you make it broader, then also with the depth you make it deeper. That still has even for the same number of iteration per iteration, you need more time. Yeah, but now the question is, in a metric, should you take iterations? Should you take execution duration? Maybe both. It's all a little bit difficult, because when you look into the detail how it's run, then for example, for the if you would just benchmark based on the duration, you might not have prioritized access. You might stand sometimes in the queue. Like, it's very interesting to benchmark like the whole system, but it may be very unreproducible from day to day, depending on how many circuits did run, how many people did have access at once. Do you have access on your own and no one interferes, and how many delays are somewhere? So yeah, it's all these things to consider and to learn when looking deeply into these things, and to think about how is it good to benchmark this. And yeah, now let's run it on a trapped ion quantum computer. The first thing you have to go for is choose some training data. That's also a very difficult point, and we intentionally looked at imbalanced data and balanced data, which I will show you now, because it's so important what your data input is. You can take a lot of effort for thinking about the classical optimizer, thinking about the quantum ansatz, and then still screw it up by a choice of the training input data, because you can only use so little data. That's really a bottleneck in nowadays quantum computers. So this has to be very carefully chosen to actually think about, yeah, is this running well on your quantum computer? Here you see an imbalanced set, so it's a classifier. You have this 2D feature space, x and y, in the left plot. And you have this line where it's linearly separated, and on the bottom the green dots are one class and the blues are another class. And now we have these ansatz. I showed you the circuit earlier, and you train it on the quantum computer, and this is data from the hardware. You do it for the different depths. It's the function evaluation here, what you get then, and it's nicely converging. And then on the right part, you see behind the curtain also the nasty things happening on hardware. Sometimes it just fails because something goes wrong on the hardware. And then suddenly, for example, here a laser was out of lock. You just get very different results out of a hardware reason, yeah? And usually if a user wouldn't see that and there's just like a very different result maybe coming, I don't know, maybe it's about the hardware, maybe it's about my answer, it's something going wrong in the optimization. But here you see, this is a hardware thing, which can be also catched in the hardware, but then what is very important is that once it's fixed, you resume again from the old good point. So this is really a challenge to get together there and work together from both sides, knowing what you want to do, but also how you do it, to catch these things and to build it in a way that once you start optimizing, because these things run very long, they need really lots of hours if you do a lot of optimization runs, and you need a stable system, but you also need to be able to resume later on if you had any failure in between, because it can happen. And here you see how the parameters then were optimized over the number of iterations. And as usual, first you wiggle around a lot, you search in parameter space, and then it settles and stays there. And these were 2.5 million shots on the trapped INQC red trap. They were taken, I think, in the duration of some hours over one night. And what you can also see here, that maybe we could have chosen the convergence criteria a little bit less strict because at the very end it's settling more. Still you see exactly this behavior, that it needs more iterations for the single qubit, and then for the 2 qubits it stays rather constant. And how did this perform with the, now when we test the model, we trained the model, but how does it perform? On the training data, it's really good. So if there would be any failure, it would be marked in red. And you see, we trained very well on the training data. We characterized that very good, but the test data, a huge test data set, is not so well classified. And that is not because it didn't converge very well, or our model is not trained so well, it's rather overtrained on this not so well chosen input data set, which we know also from is a problem in classical machine learning. And you can see on this test data, if you would put a horizontal line in there, which would also very well separate the test data set, then it would actually work quite nice. So it's a thing to consider always also when you then later on judge how good the quantum computer was during your job, then maybe it's due to a reason like the training data. This is how this looks now for the trapped INQC results. And you can also compare it then with the simulation and have a look if this meets your expectations there. And now we did this also with balanced data. So now we have in each set 5 data points, and you see on the training data evaluation, there are some false classifications right close to the border of both classes, but now also on the test data evaluation, we are much better. And what I did cut out here due to the time is these curves again, how we converged. There is on the 4th one, we actually didn't end up at the minimum close to the others, but we ended up at a different minimum, converged there. And this is most likely a barren plateau. So there are many things, and people are actively working on how to avoid these barren plateaus. And this is, of course, also things you can integrate, but you also have to consider when comparing, because one thing is always, ideally you would do a lot of runs, but it's very resource intense. So how to do a lot of repetitions of these whole training sets? Yeah? You anyway need a lot of repetitions to do these optimizations, but then you also have to you should not judge it just on one generated output. So what did we do? We have a first draft for this benchmarking metric, and we see kind of expected that these results depend heavily on the training data input set, but I think it's very nice that we could reproduce this on a trapped ion quantum computer. And this rather opens also a lot of questions, and it's an interesting way how to
Maybe I can finish with one sentence. These things that we wanted to see as well in research, they wouldn't have been possible if we wouldn't have this kind of deep cooperation. A user would not have been able to solve the problems on the hardware that you need to do in order to see these things. Thank you for your
thank you very much.
support. Yeah.